In this video, we're going to practice sketching rational functions. So for example, let's say f of x equals x squared over x plus 2. So this is a rational function because it's one polynomial divided by another. So we'll go through a sequence of parts here that will lead us to making the sketch of this function. For part A, let's find any x-intercepts. There may be more than one x-intercept, and we'll also find the y-intercept if it exists of this particular function. So to start with the x-intercepts, what we're going to do is set y equal to 0 in our function, and we will solve for the x value. So if y is equal to 0, then we've got 0 equals x squared over x plus 2. We can multiply both sides by x plus 2. Well, we'll still have 0 on the left, and on the right we'll just have x squared now. So x squared is equal to 0. That tells us that x is equal to 0. So the only x-intercept that we get is the point 0, 0, where x is equal to 0 and y is equal to 0. For our y-intercept, to find the y-intercept in general, what you do is you set x equal to 0 and solve for your y value. So in this case, y is going to equal, well, 0 squared over 0 plus 2. So y works out to 0 over 2, or in other words, just 0. So when we set x equal to 0, we get y equals 0. In fact, this just gives us the same point that we just found in the previous part of the question. So just the point 0, 0, that's our only intercept for this particular function. For part B, we're going to look for any vertical asymptotes for our function. So here we're looking for x values where our function is undefined. So if we go back to our original function and we just grab the denominator here, we're going to set the denominator equal to 0. So x plus 2 is equal to 0. That corresponds to x equal negative 2. So x equal negative 2 is a vertical line. It's a vertical asymptote for this function because it's an x value where the function is undefined. For part C, we're going to look for any slant or horizontal asymptotes. Okay, so a function can have a slant asymptote or a horizontal asymptote, or in some cases, neither. So to figure out whether we have one of these types of asymptotes, we're going to take the limit as x goes to plus or minus infinity of our function. So of x squared over x plus 2. So if we think back to the beginning of the course, we saw the technique on how to handle these types of limits as x goes to plus or minus infinity. And the trick is to look for the highest power of x that is in the denominator. So highest power of x in the denominator here is x. We're going to divide every single term in the numerator and the denominator by x. So this is equal to the limit as x goes to plus or minus infinity of x squared over x divided by x over x plus 2 over x. Okay, and now we can do a little bit more simplifying. We've got the limit as x goes to plus or minus infinity of x over 1 plus 2 over x. So that is now as simplified as we can make it. Now imagine what happens as x gets really big. So if you imagine x values of say 1,000,000 or 1,000,000,000, this expression here, this 2 over x, is going to 0. And even if you were to take very negative numbers like -1,000,000, -1,000,000,000, this expression is getting closer and closer to 0 as x gets bigger and bigger. Whether x is positive or negative doesn't affect this. So either way, this term is going to 0. So what we've really got then is the limit as x goes to plus or minus infinity of really just x, because we've got x over 1 plus 0. So just simply x. Okay, so in this case, we do have what's called a slant asymptote. And its equation is just y equals x. So we get the x here from this simplified value that we've calculated through the limit. Slant asymptote, y equals x in this case. So we'll be able to see what that looks like towards the end of the question when we actually do the sketch of our function. We'll be able to draw this slant asymptote on and see that as x gets very big, so as x gets close to infinity or close to negative infinity, our graph is approaching this line. So the general rule is that once you've got this expression simplified here, if you end up with something that looks like ax plus b, where a is not equal to 0, so as long as you've got any real number times x plus some other real number, so for example x or 2x or 2x minus 1, in all of these cases you get what's called a slant asymptote. And the equation of your slant asymptote is just y equals whatever this expression is. So in this case we had the slant asymptote y equals x. If we instead had found that our limit simplifies to just a number, so just the number 0 or 1 or 2 for example, then we'd have what's called a horizontal asymptote. So then you'd have the equation y equals whatever your number is. And depending on your function, you may end up with neither of these situations. So otherwise, for example, your function might simplify to something like x squared or x squared plus 1. So if you get any other type of situation, then we just say, no, there's none. There's no slant asymptotes. There's no horizontal asymptotes. So those are the 3 situations that we can run into. Any relative maxima or minima. So we're going to find any relative maximum points or minimum points. And this comes down to looking at f prime of x. So in this case, we've had a lot of examples or a lot of practice with using the quotient rule. So I'm just going to write down what the derivative works out to. And I would encourage you to pause the video and just check this work, try using the quotient rule yourself and make sure that you can come up with this derivative. So f prime of x comes out to x squared plus 4x over x plus 2 all squared. And I'm going to write check this because I really do encourage you to go through the calculation there, do a little bit of simplifying and make sure that you can come up with this derivative. Critical points. We are looking for places where f prime of x is equal to 0 or undefined. So I'm going to underline this here. This definition is a little bit more general than what we were using when we were sketching polynomials. If we think back to what we did with polynomials, we automatically just set f prime of x equal to 0. Well, that worked for polynomials because polynomials are never undefined. So now there's this extra catch that when we're working with rational functions, we need to think about x values that are going to make the denominator equal to 0 as well. So we're thinking about where's the numerator equal to 0, where's the denominator equal to 0. The reason is we're trying to think about places where our derivative can change signs. So it can change signs anywhere where the numerator is 0 or the denominator is 0. So let's try to remember this general definition here. Okay, well, in order to do that, it would help to get our derivative factored here. Let's think about factoring the numerator. We could pull out an x there and make it x times x plus 4. Oops. X times x plus 4. And the denominator is already factored for us. So we would like this to equal 0 or undefined. All right, so let's just think about taking the numerator, setting it to 0, taking the denominator, setting it to 0, and we'll get a list of x values for each situation. So in this case, x could equal 0 or -4. From setting our denominator equal to 0, we get the critical point -2. Okay, so we're now going to draw a number line incorporating our 3 critical points here. So -4, -2, and 0. And remember that these are the only places where f prime of x can change signs. So our goal is to figure out what the sign of f prime of x is on each of these little intervals. So for each of these little 4 intervals here, we're just going to select an x value in the interval. So for example, in this first interval, we could choose -5. We're going to plug that into our derivative and just figure out the sign of our derivative. So if we plug -5 into our derivative, we come up with a positive value. So f prime of x is positive. And because f prime of x cannot change signs anywhere except at these critical points, we know f prime of x is positive on this entire interval. Okay, so for our second interval, we could test, say, -3. You can check that you'll get a negative number if you plug that into our derivative. Maybe choose -1 for the third interval. Again, you'll get a negative value for the derivative. And maybe here in our last interval, you could try plugging in 1 or 2, any x value in this interval, and you will come up with a positive value for the derivative. So what that tells us about our function itself is that our function is increasing on that first interval. So first derivative being positive corresponds to the function increasing. Function is also increasing from x values from 0 to infinity. And our function will be decreasing in these middle 2 intervals there. So to answer the question about whether there are any relative maxima or relative minima, well, we're going to have a relative maximum over here where our function moves from increasing to decreasing, and we're going to have a relative minimum over here where our function moves from decreasing to increasing. Okay, if our function goes from decreasing to decreasing, that doesn't correspond to a maximum or a minimum. So 2 points to answer the question. We've got a relative max, and that happens when x is equal to -4. We've got a relative min when x is equal to 0. So we're going to have to plug both of these x values here back into our original function to get the y values. Remember, we're going to use these points when we are graphing the function. So we really want to make sure this corresponds to f of 0 and that this one over here is f of -4. So going back to our original function, our y value here is -8, and for this point here, f of 0 is equal to 0. Okay, so that gives us 2 points. That answers the question, and we'll use these points later on when we make a sketch of our function.